Hey everyone, welcome back to physics. This will be lecture 10 of the course. And in this section, we're going to discuss, we're going to start looking at how to think about and solve problems that involve different reference frames. So we're going to be talking specifically about relative position, relative velocity, and relative acceleration. So let's go ahead and jump into it. And we'll really call the section 2.4 relative velocity. And so in order to kind of develop this properly, I think we want to start with the idea of relative position just to level set on some things. Okay, and so we'll start with relative position. Okay, so what we're going to, the kind of the mental exercise that I want to go through here is we want to think about a ball, just an object, we'll just call it a ball, but we're going to think about it from the standpoint of two different reference frames. So consider a ball in two different reference frames. Right, and what are those reference frames? Well, we're going to call them the lab frame, which we'll denote with an L. And then the second frame will be the Richard frame, i.e. me. The Richard frame, which we'll denote with an R. Okay, and we'll start by, it's important to note there's a hierarchy to these frames to some extent. So start by noting the fact that the lab frame is the main coordinate system, right? And you can think of this as kind of straightforward if you think about it like, look, both Richard and the ball are inside the lab, right? The lab is not contained inside the Richard frame, right? It's the reverse, right? So there's this kind of ground frame, which we'll think of in this example as being the lab, right? And so we can start by just kind of drawing in a coordinate system that is meant to indicate the lab frame. Okay, so we've got the lab frame. All right. Now, inside the lab, we have Richard and we have the ball. And so let's place the Richard frame inside the lab frame next. And so the Richard frame is a frame, right? So that means it's got its own coordinate system. Right? As Richard moves around the frame, things move in relation to Richard as well, right? And then finally, let's put the ball in here. We'll put the ball up in this section somewhere. Right, so I'll just write ball. Okay, so you've got these three objects. So you've got the lab frame, and then you've got Richard and the ball inserted into the lab frame. Right, and now we can draw in the position vectors for these two. Right, so the first one we'll put like this. This will be, we'll denote it as R, position of the ball relative to the lab. So we'll use a B, L subscript. So that's the position of the ball in the lab frame. Now we can also draw in a position of Richard in the lab frame, right? That's just going to be another vector. And so again, this is the position, but now it's of Richard inside the lab, so R, L. Right, and then finally the ball exists inside the Richard frame as well, right? And we can draw a position vector for that. All right, so the position vector here would be denoted R for position, and then it's the ball, B, inside the Richard frame, so comma R. Okay, and so this is a really helpful framework when you're doing relative motion kinds of problems, right? Start with this idea that you've got a main frame, and then you may have several other frames existing inside that main frame, or just objects existing inside that frame. So here we have the main frame, which is the lab, and then we have the Richard frame, which is a frame of reference inside the lab, and then we have the ball, which is an object inside the lab. Okay, so let's go ahead and denote, let's write out what all of these things are just to make sure that we're very thorough here. So R, B, L, that is the position of the ball in the lab frame. Okay, and then next we have R, L, That's the position of Richard in the lab frame. And finally, we would have the position of the ball inside the Richard frame. Right? So these are just position vectors, right? Now, it's tempting to want to say that the ball is not inside the Richard frame, but no, this is just a coordinate system, right? It's a three-dimensional coordinate system technically, right? And so the ball just happens to be in the negative side of the Richard frame. So I could easily extend this axis over. I could extend this axis down, right? So just think of this is a three-dimensional coordinate system, as is the lab frame. The ball exists somewhere in both, right? They're just relative to one another. Okay, now as you kind of look at this, it should be pretty clear that these vectors are all related, right? And specifically, we could say that the position of the ball in the lab frame is equal to the position of Richard in the lab frame plus the position of the ball in the Richard frame. Right, so the ball in the lab frame, this piece here, could be got to by taking this plus this, right, specifically. And then, of course, you can do arithmetic maneuvers on that to kind of solve for any one of the three. Right, but this is how they're kind of related. Now, once you have the position relationship, you can easily derive the velocity and the acceleration just using differentiation as per usual. Right, so this same relationship is going to hold for the velocity vectors. So velocity of the ball in the lab is equal to the velocity of Richard in the lab plus the velocity of the ball relative to Richard. And acceleration as well. Acceleration of the ball in the lab is equal to acceleration of Richard in the lab plus acceleration of the ball relative to Richard. All right, so these things are just derivatives. Okay. Easy enough. Okay, now let's just kind of extend this this idea a little bit and think about what we call these, relative velocities, right? So the velocity in one frame of reference is going to vary depending on, what frame of reference the observer is in, et cetera, right? So let's think about it. Let's have kind of a simple, sort of mental exercise. What happens if Richard is walking forward, we'll say, at 1 meter per second in the lab frame? Okay, so let's just kind of think this through here. I'm going to redraw this a little bit, not entirely. Right, so we've got the L frame. And then we've got the Richard frame, right, which is the smaller frame inside here, which we'll call R frame. Now let's say this entire frame here, the Richard frame, is moving, right? So the velocity of Richard relative to the lab is 1 meter per second. Okay, and then we've also got the ball in here, right? Okay. So the Richard in the lab velocity, Richard relative to the lab velocity, is 1 meter per second. Now, in this case, from the standpoint of Richard, from my standpoint, if I'm walking in 1 meter per second in this direction, it's going to look to me like the ball is moving away from me, right? The ball is going to appear to be moving in the opposite direction. Right now, even though the ball is actually stationary inside the lab, it's not in motion at all, right? So how does this all work out, mathematically? Well, start with our velocity equation. Velocity of the ball in the lab is equal to the velocity of the ball relative to Richard plus the velocity of Richard relative to the lab. Okay. Now, in this example where the only thing moving is Richard relative to the lab frame, I'm moving at 1 meter per second to the right. We know that the velocity of the ball in the lab is equal to 0. right? The velocity of the ball relative to Richard, that's sort of the thing we're questioning. We're wondering about that. It kind of looks like the ball is moving backwards, but we know it isn't. But inside the lab, I'm actually moving at 1 meter per second. Right, so we get kind of this expression, right, if we just kind of plug in these values. So the ball is not moving at 0 meters per second relative to the lab. Richard is moving at 1 meter per second relative to the lab. So what does that imply that the ball is doing relative to Richard? Well, the implication here is that the velocity of the ball relative to Richard is equal to -1 meters per second. Right, you just do a little algebra on this. You basically subtract 1 meter per second on both sides. And so even though the ball is stationary in the lab, from the standpoint of the Richard reference frame, the ball with respect to Richard is actually moving away from me. Right? So this is kind of how it all works out in the mathematics. Okay? And so this kind of expression here is really what we wanted to flesh out in this section. Now let's do an example, a little more complicated example of how this kind of thinking can be used to solve problems when you have different reference frames. Okay, so here's an example. This is a standard kind of example, but it's a really good one because it's intuitive. People have experience with it. It's also like accessible for beginners, right? So we want to consider a boat. Consider a boat lined up with a dock. Consider a boat lined up with a dock across a 20-meter wide river. Okay. And so let me start to draw this picture here. All right, so you've got a river. This is my river. It's 20 meters across. And we've got a boat lined up with a dock. So there's the dock, D, and the boat is over here, B. Okay, so they're perfectly aligned. Okay. So if the water is flowing at 3 meters per second, what is the boat's velocity in the land frame when it is moving 5 meters per second perpendicular to the shore? Okay, so kind of a wordy idea here, but basically you've got the water frame here, right? The water is flowing, right? And so the water is moving at 3 meters per second. The boat is said to have a 5 meter per second velocity perpendicular to the shore. What that basically means is it's just going like this, straight across. Right, but obviously as the boat is moving in that direction, the water is going to take it downstream, right? So the boat may be moving at 5 meters per second across the river, but it's also moving 3 meters per second down the river. So it's got more like a kind of a diagonal sort of motion. So it's kind of going to be going more like this. Okay. Right, so the boat's velocity is actually 5 meters per second relative to the water, right? So it's moving, cutting through the water at 5 meters per second. But it's also being dragged at 3 meters per second downstream, right? So hopefully that's clear. Like the boat is going to sort of, it's not just going to go straight across the river because the water's dragging it downstream. So it's going to kind of go more like this. Okay. So what are the frames here? Well, the first one is the land frame, right? That's basically, the shore, right? The dock. Those are in the land frame. The second one is the water frame, which we've noted here. And then the third frame of reference is kind of the boat frame, although I don't really know if that's a frame of reference. It's more like an object in the L and W frames. Okay. All right. So what is the velocity? What we're interested in knowing is we've got the velocity of the boat relative to the water. We've got the velocity of the water relative to the land. We need to know what the velocity of the boat relative to the land is. So we can use velocity of boat relative to the land. That's what we're interested in. And so that's going to be the velocity of the boat relative to something plus the velocity of something relative to the land, right? So the B goes here, and we got to figure out what the intermediate thing is. Well, it's obvious that the intermediate thing here is the water, right? All right, so we kind of fill those in. So what is the velocity of the boat relative to the water? Well, we just said that the boat is moving through the water at 5 meters per second. Okay, and what's the velocity of the water relative to the land? Well, it's given that the water relative to the land is 3 meters per second. Now, because this is all being kind of translated into the land frame, we really need to kind of have a coordinate system for the land frame. And so what we're going to do is we're going to think of the land frame as having an XY orientation like this. Right, very intuitive, natural. Right, so that means that the 5 meters per second, that's the J direction. And the 3 meters per second, that's the I hat direction. Right, so the velocity of the boat relative to the land is this. Right, it's a vector. Right, it's a vector. It has both magnitude and direction. The direction, namely, captures this drift downstream. So the velocity of the boat relative to the land would be more like a vector, kind of off in this direction, wouldn't it? Right, it'd be kind of look more like this. Right, so 3I plus 5J, basically. All right. Okay, so that's the first part of the question, right? This sort of sets up how, you've got velocity in the water frame, also velocity in the land frame. You kind of combine those things to get the velocity of the boat in the land frame. Okay, what if, so if the boat moves in this way, we know clearly it's going to cross the river, but as in crossing the river, it's going to drift downstream. So the next question would be, by how much is the boat going to miss the dock? It starts perfectly aligned, so it's obviously not going to land at the dock. It's going to land some distance downstream. So what we want to know is how far downstream does the boat actually hit the opposite shore? So if the boat moves in this way, so if the boat moves in this way, by how much will it miss the dock? Okay, so by how much will it miss the dock if it moves in this way? Well, this is actually super easy to answer, right? To kind of answer this, there's different ways to answer the question. One really easy way to answer this question is to say, look, how long, we know the boat's going to move across the water at 5 meters per second. How long does it take it to get across the river then, right? It's going to go in this direction, 5 meters per second. Well, it's a 20 meter wide river, so how long is that going to take? Delta T here would just be the distance across the river, 20 meters, divided by how fast it's moving across the river, which we're told is 5 meters per second. And you do that math, and you see that it's just going to take 4 seconds for the boat to reach the opposite shore. Okay. Now, again, it's not going to reach the opposite shore at the dock. It's going to reach the opposite shore somewhere down here. And so how far down here will it be? Well, it's moving at 3 meters per second downstream. So if it takes 4 seconds before it hits the opposite shore, that, multiply those two together. So delta X, we'll say, the distance downshore, is just going to be equal to, in this case, 3 meters per second that it's moving downstream times the 4 seconds it'll be moving across the river. And so it's going to land 12 meters approximately off the dock. So this is going to be 12 meters. Right? It'll miss the dock by about 12 meters. Okay. All right. Very good. Okay. So, and then the final question here, look, if this is an experienced boat driver, this guy's going to know, look, I can't just go straight across and hit the dock. I'm going to have to angle my my 5 meters per second upstream somewhat, right? So if the boat wants to hit the dock, at what angle should it steer? Right? So the boat driver has control over which direction the boat moves, right? Which direction the 5 meters per second is directed, right? So basically, you know, if you have, again, the river here, and here's the dock, and you're starting opposite the dock, right? So here's like the straight line across the river. If you're starting here, you're going to want to angle that 5 meters per second upstream somewhat, right? And so the question is, what should we set theta to in this example such that the boat actually lands at the dock, right? So basically we need the velocity in the I direction to completely cancel out the velocity due to the water. Okay, so rather than moving at 5 meters per second perpendicular to the bank, the boat should aim upstream somewhat so that it lands on the dock, right? So I'll just write that in. That's the main idea here. Rather than moving at 5 meters per second perpendicular to the bank, the boat should aim, we'll say, upstream. Okay. All right, so let's think about this in terms of our relative velocity equation. So we've got velocity of the boat relative to the land is equal to the velocity of the boat relative to the water plus the velocity of the water relative to the land. Okay, so this part here specifically is what we want to change. We want to change this part. Okay. This part here, I mean, we can't influence the velocity of the water relative to the land. That we're stuck with, and we said that before that is 3 meters per second I hat, right? Okay, so we know that the boat's going to be traveling at 5 meters per second through the water, so we just need to figure out what direction to send the boat. Right, so we can kind of think of this in terms of a triangle. Right, so here's our theta, right, kind of aligns with this little thing here. And so this is 5 meters per second, and this will be like the opposite side relative to theta, and this will be the adjacent side relative to theta. Right, and so we can just we want an expression that involves theta because we want to vary theta such that we land on the dock. Right, and so the I direction can be figured out using the sine of theta is equal to opposite over hypotenuse. Okay, and the implication then is that opposite side, this side here, meaning the I component of the boat's velocity, is equal to 5 sine of theta. Now, important to note that the way we've coordinatized the land, we have, you know, x, y like this. So this would be in the negative direction. So this needs to be negative. So this guy here should be negative 5 sine theta. And what about in the j direction? Well, there we'll use the cosine of theta equals a over 5. And so, of course, a would be equal to 5 cos theta. Now that is going to be in the positive direction. So we're moving, here we'll be moving up like this and over like this. So those are positive and that's negative. Right? So we've got these two expressions here. And we're just going to plug these guys in for the velocity of the boat relative to the water. This is the velocity that we want to be able to adjust. Right? So the velocity of the boat relative to the land is equal to, again, just recapping this, boat relative to the water plus velocity of water relative to land. Right? And so rather than just go with 5 meters per second in the j direction, we're going to break it apart. And we're going to write, instead we're going to write 5 5 cos theta, sorry, we're going to write, we'll start with the negative. Negative 5 sine of theta in the I hat direction. That's the x direction, that's this. Plus 5 cos theta in the j hat direction, right? And so that's this part. And then we've also got this guy here. We've got the water, which is highly relevant, so we need 3 I hat. Okay, sorry about that. Let's pull that up there. Okay, so that's the equation. So if I want the velocity of the boat relative to the land, I can use this expression, which if we set theta equal to 0, then this is what we would get, right? We would just have 5j plus 3i, right? But we want to be able to vary theta. So the question is, how do we figure out what theta needs to be so that we land at the dock? So how do we figure out what theta needs to be in order to land at the dock? Well, you got to think about, like, what does it mean to land at the dock? Right, so going back up to this picture here. We saw before, that, well, I'll draw a new picture. A lot of times the harder part of physics is kind of thinking about how to ask the equations for the right answer, right? So if I've got the shore here and I've got the dock, now normally the boat is going to go like this, right? It's going to kind of make its way across the river, but also downstream. But what I want instead is I want the boat to just go straight across, right? So one way to say this is to say that I want the velocity in the I direction to be 0. I don't want to move at all in the I direction. I just want to move in the j direction. So we want the velocity in the I direction to be 0. Okay? If the velocity in the I direction is 0, that means the velocity is all in the j direction, right? But we have to kind of counteract this 3 here, right? So this 3 here is going to try to drag us downstream. So whatever we plug in for theta, it needs to completely counteract this, right? So basically this needs to equal -3, right? So another way to do it is to just say, look, I want the I component to equal 0 and then figure out what theta needs to be. And that's what we're going to do. Okay, so we're just going to solve a simple little expression here. We're going to we want to set the I component equal to 0 and solve for theta, right? So we've got 0 meters per second is equal to -5 sine of theta plus 3, and this couldn't be easier, right? The sine of theta is therefore 3/5, and so then if you just look at the inverse sine function, you'll see that theta needs to be approximately 30.5 degrees, right? And so in our scenario here, the boat will actually move like this, right? It'll kind of be offset at an angle, and in doing that, it'll stay just ahead of the current. The current will try to drag it down, but because its heading is a little different, it'll offset the current. The motor, namely, will offset the current and keep the boat in line with the dock. Right? And that works when this theta here is 30.5 degrees. Okay, very good. All right, so that's an example of relative velocity. So you've got different frames, velocities in different frames. How do they combine, and how can you solve problems using those combinations, right? So That'll do it for this section. The next lecture is going to be problems and examples, so we'll be revisiting a lot of the section 2 two-dimensional two-dimensional kinematics, basically. We'll be revisiting a bunch of those problems. So we'll see more relative velocity problems, we'll see more circular motion problems, and we'll see projectile motion and other just random two-dimensional problem types in the next lecture. All right, take care.